The moon has captivated human imagination for centuries, but what if I told you it's also a goldmine of untapped resources? From fueling deep space missions to powering the next energy revolution on Earth, the moon could be the key to our future in space. So, what treasures lie hidden beneath its dusty surface? And how can we turn the moon into humanity's stepping stone into the cosmos? Let's find out. To understand the moon's resource potential, we first need to uncover its past. Scientists believe the moon was born from a cataclysmic collision between Earth and a Mars-sized protoplanet called Theia. This massive impact scattered debris into orbit, which eventually coalesced to form our moon. As the molten moon cooled, a process known as lunar differentiation occurred. Heavier materials sank, creating an iron-rich core, while lighter minerals floated to the surface, forming the crust. This led to the development of distinct internal layers like a small and iron-rich metallic core, with some indications that it still remains partially molten. And other layers including a mantle, composed mainly of silicate minerals like olivine and pyroxene, similar to Earth's mantle, and crust predominantly made of feldspar minerals, forming the bright lunar highlands. These highlands consist mainly of anorthosite, a rock composed primarily of plagioclase feldspar. They are among the oldest parts of the moon, dating back 4.4 billion years. Formed from the cooling of the original lunar magma ocean, they provide a glimpse into the moon's early history. Lunar Maria, on the other hand, are dark, flat plains created by ancient volcanic activity. Made mostly of basalt, rich in iron and magnesium, formed from lava flows that rose through cracks and fissures in the already solidified crust during a geologically active period between 3.9 and 3.2 billion years ago. The difference between these two geological terrain types can be mapped with the naked eye. The next time you have a look at the moon, pay attention to the lighter and darker colored parts. The lighter areas represent the lunar highlands, and the darker colored areas the Marias. Compared to Earth, the moon also appears littered with impact craters, signs of our solar system's sometimes violent past. On the moon, these craters are better preserved as they are exposed neither to erosion nor plate tectonics, processes that constantly reshape the surface of Earth. And what about the resources that are hidden in our night sky? It's important to understand that not everything we mine on Earth can be found on the moon. Our satellite only hosts a fraction of the resources we can find back home. However, these lunar resources are crucial for humanity's spacefaring ambitions and could, in one case, even be exported to Earth. Exporting raw material back to Earth is often not a viable option, as the transport costs, even with the latest, reusable rockets, are simply far too great. There is, however, one substance that is so valuable that a few grams are likely enough to pay for the transport back to Earth. The commodity in question is helium-3, a rare isotope virtually non-existent on Earth, but abundant in the moon's soil, the so-called lunar regolith. This element is a potential game-changer for clean energy, offering a safer, radiation-free fuel for nuclear fusion. Imagine a world powered by lunar energy. No radioactive waste, just pure, limitless power. The energy that could be released via nuclear fusions is so great that just a few kilograms of helium-3 could be enough to produce the equivalent of an average nuclear power plant's annual output. But that's not all the moon has to offer. There are more treasures hidden in its soil. Perhaps even more valuable than helium-3 are large amounts of water ice that remain frozen in the regolith at the depth of ancient impact craters, mostly around the lunar South Pole. The existence of ice on the moon is a game-changer as it will allow future moon bases to produce drinking water, oxygen, and rocket fuel by splitting the water molecule into its atoms. Then, there is, for example, ilmenite, a titanium iron-rich mineral that can be found in the mafic rocks of the Lunar Maria and their corresponding regolith. Extracting iron and titanium from this mineral can come in very handy for building spacecraft or lunar bases on the Moon, as the transport of large quantities of these heavy metals from Earth would simply be impossible. The lunar regolith is also heavily researched for its potential use as a building material for lunar infrastructure and housing by applying novel 3D printing technologies. With plans for a long-term lunar presence gaining momentum, space agencies and private companies are actively working on strategies to establish permanent infrastructure. Imagine a future where humans don't just visit the Moon, but live and work there, a reality that no longer belongs solely to the realm of science fiction. As interest in lunar exploration grows, so does the vision for a sustainable presence, with NASA currently aiming to send astronauts back to the Moon in 2027. A lunar base could serve as a launch pad for interplanetary exploration, drastically reducing the cost and energy required for deep space missions. Imagine spacecraft refueling on the Moon or in its orbit before heading to Mars and beyond. With its untapped resources and strategic location, Moon exploration could revolutionize space travel, energy production, and even life beyond Earth. The next few decades will shape the future of lunar exploration and perhaps humanity's destiny among the stars. What do you think? Let us know in the comments. Until next time, keep looking up.